All right, welcome everybody. Looks like we're ready to go. So last day of the course, at least last meeting, you still have a little bit of time to work on some homework assignments. But good job making it to the end. So these summer courses are hard. They move so fast, and not everyone who signed up for this course has made it to the end. So good job for making it to the end. It's definitely an accomplishment. Hopefully everything will turn out and I can give as many passing grades as possible. Excuse me. So make sure you keep working on the homework. I've been giving out the late passes. In fact, let me just double check. Let me pull this off screen here so I'm not showing anything that I shouldn't. Anything private or student privacy, basically. So let me just double check. I'm amazed at the pace at which some people are going through the... Okay, it looks like we're good. Going through the late passes, but that's fine, right? I'm glad people are doing their homework, so that's great. Like yesterday, I reset everyone's late passes to 20, and then by the afternoon, some people were out of late passes. So that's great. Get those homework points. Those homework points are going to help you in the end. One way or another, they're going to help you. So that's great. I'm happy to keep doing that. The grades will get. Basically, I'm going to try to collect grades the test tomorrow when the testing center is closing. I'll probably my goal is to get grades submitted on Sunday. They'll be available to you Monday. It might be one day later. I might get grades submitted Monday, and then they're available to you on either late Monday or early Tuesday. So that's how that works. Let's see. I believe, so there's a question here about the practice test. I think the problem on the practice test was just to set up the matrix, wasn't it? Let me see. I think so. Let's see the thing. Problem 8 here. Yeah, so what matrix should be used to represent the following system of equations? So yeah, I don't need you to use the matrix in order to solve the problem here. I'm just looking for, can you set up the matrix? Like, can you give me the proper matrix that represents this system of equations? So not all that complicated stuff where you're doing row echelon form or reduced row echelon form and Gauss-Jordan elimination and all that kind of stuff. Just show me what matrix represents the system of equation is what I'm looking for there. Okay, great. Great. So we just have a little bit less to cover. Remember, the exam will not cover sequences in series, which is what we're covering today. You should do the homework for sequences in series, get those points, but it won't be on the exam. And just so everyone knows, hopefully this gives you a little bit of, or lets the stress off a little bit. When I take everyone's homework grade from XYZ homework, I usually like at least round it up, and sometimes I throw in an extra % or two, just because I know some of you along the way had difficulty entering an answer in the way that XYZ homework wanted it, or you didn't quite understand the directions. And I have seen a couple of questions in the XYZ homework, well, I'll admit, it was kind of weird the way they were asking for the answer to be presented. So I know that was confusing for some students. So, those points add up to almost nothing. When you consider the number of homework points you've attempted over this entire course, a couple of problems here and there won't really affect your grade. But I always kind of bump things up just slightly, not a lot. But like your homework grade might get bumped up 1 or 2% just to make sure that it's more than compensated for any difficulties that people had along the way using the homework, right? So if there was one problem, 10 days ago that you feel like you got cheated out of, don't worry. You'll get a little bit of, some extra points in the homework score in order to balance all that kind of stuff out. So don't let that stress you out. You should be stressing out about other things, not like the fact that the homework platform may have cheated you out of a couple points. So there's that. Just get those assignments done, right? Work on those. Like I say, I don't think I'll pull those grades before Sunday unless something weird happens. So Sunday is the day that I'm probably going to take those homework grades, and they'll actually become like set in stone, where I'll actually put them into the grade sheet that I create in order to go through and do all this stuff. So that's how that will work. And then, grades should be available to you either Monday or Tuesday, probably Tuesday or late Monday, inside your portal. So if you go into the VC portal, you should be able to see those grades in there. Okay. So if there's no other questions, let's dive into the homework. So you've got the last bit that's due tomorrow. Sequences and series it's different than the kind of stuff we've been doing so far, but a lot of people kind of get it. It's okay if you don't get it. Some people find it confusing. But it's one of those things where there's some formulas. The hard parts have some formulas that help you do the problems. And the good news is most of the formulas are pretty easy to use. They're not like really complicated formulas that are confusing. It's like if you know where things go, the actual computation is pretty easy. Like one of the formulas we're going to use, it's like a subtraction and a division, so that's not very complicated. So let's kind of dive into this. Let's see, here we go. Oops, that's the conic sections. Chapter 7, sequences. So we have this definition. Sometimes I think when we first introduce topics, we sort of make them more complicated than they need to be. If you want to know the question, well, what is a sequence? Because we're going to learn about different types of sequences. You can see right down here, they're already getting to arithmetic sequences, and then later we'll look at geometric sequences. But you can just have general sequences. And this definition right here seems kind of complicated. And it's a good definition. We use this. It's helpful. But it's nice to have a way of just thinking about, well, what is actually a sequence? And a sequence, the easiest way to think about a sequence is that it is an infinite list of things, an infinite ordered list of things. It has a specific order. So like a set, if you have in mathematics a set, you can rearrange the terms in a set, and it's the same set. The order doesn't make any difference, right? You think of a set as like a bag of something. If you jumble up the bag, it's still the same items in the bag, right? But a sequence is where you have an infinite list of things, and they're in a specific order. And usually, like for most of what we do in here, those things will be numbers. Okay, so that even simplifies it a little bit more. We will be talking about an infinite list of numbers for the most part. I forget if there's a problem or two in here where we look at we have infinite lists of something else. But you could have a sequence of functions, right? You can have each function be a different function, and you just have an infinite list of those things, right? You could have an infinite list of any mathematical object. You can have an infinite list of matrices, right? You could have a sequence of matrices. So you can get really fancy with sequences, although for the most part in this class, we're going to restrict ourselves to sequences of numbers, which greatly simplifies it, right? Some of you later on, if you're doing computer science or math or certain areas of physics or something, you might get into sequences of other types of objects. Especially if you end up in graduate school or something. But in the foreseeable future, between this and the stuff you're going to do in, say, a calculus class, like Calc 1 and Calc 2, generally your sequences are going to be numbers, right? So let's read the definition. With that understanding, let's dive into the formal definition. A sequence is a function f of n whose domain is the set of all non-negative integers, i.e. n equals 0, 1, 2, 3. So basically just your counting numbers that you use, right? The non-negative integers. So your domain, the things you're mapping from, are 0, 1, 2, 3, and whose range is a subset of the set of all real numbers. The numbers being, they call it f of 0, f of 1, f of 2, are called the terms of the sequence. So that sounds way more confusing than what I just said. But what you do is you basically have a function that turns 0 into some number, which you call f of 0. It turns 1 into some number, which you call f of 1. It turns 2 into some number that you call f of 2. So basically it's taking this set of numbers that we're very used to, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and so on, and it turns them into some other numbers. Now, do be careful. If you look elsewhere, there's two ways that books represent sequences, and this is the one that's slightly less common. Oftentimes, if you look somewhere else, sequences, they'll start with the number 1, 2, 3 instead of starting with 0. And that just changes the formulas ever so slightly. So if you look somewhere else or you look on a YouTube video and you go, wait, the formula's not matching up, that's why, right? That's because some people start their sequences with the domain being 0, 1, 2, 3. Some start with 1, 2, 3. I kind of prefer 1, 2, 3. I think it makes certain parts easier and it makes other parts more complicated. So it doesn't really matter which one you use, right? And then generally what we do is we represent a term in the sequence by a sub n. So a sub n means it's representing the nth term in the sequence. So a sub 50 would be the 50th term in the sequence. A sub 77 would be the 77th term in the sequence, and so on. Okay? So we sometimes drop this function notation. So that's why it's sometimes silly we even define it that way, because then we immediately stop using that notation, right? But you will see both notations come up, but it's much more common to see the a sub n notation than the f of n notation. But you can use either one. It doesn't really matter. Okay, so there's two big types of sequences we're going to look at. The first one is called arithmetic sequences, and the second one is called geometric sequences. And they have some similarities and some differences. So if you understand one, it's going to help you understand the other, but they are fundamentally different types of sequences. Okay, so let's take a look. Our definition for an arithmetic sequence says that each term of an arithmetic sequence is given by the rule a sub n. So the nth term of the sequence is given by the first term of the sequence plus some multiple of a number d, where that multiple is the whatever number term that is in the sequence. So this, when you start off, n is 0. Then for the next term, n is 1. Then n is 2. Then n is 3. Then n is 4, and so on. And what is this d? This d is just some value that was picked for that specific sequence. So here's basically the easier way to think about an arithmetic sequence, is that to get the next term in the sequence, you add a specific number, and that number that you're adding is the same for the entire sequence. So you might have a sequence that starts with the number 7, and the way that you always get the next term is by adding 3. So a sequence like that would go 7, 10, 13, 16, 19, 22, right? You start at one specific number, and that number that you start with does not have to be the same as the that term that's what's called the common difference, is that number that you always add to get the next term. So you start at, say, 7, and then you add 3 to get the next term, add 3 to get the next term, add 3 to get the next term. Or you could start at 4, and then add 12 to get the next term, add 12 to get the next term, add 12 to get the next term. That's all an arithmetic sequence is. Arithmetic, it's like we're adding things together. We're doing arithmetic. That's all it means. Keep adding that same difference, what we call the common difference, to get the next term. These are generally pretty easy to analyze and to deal with. Well, they're new to you at first, but you can kind of get the sense of it. So here, use the first few terms to find the rule. So a lot of times you'll be doing this. You'll be trying to find the rule for a given sequence. And what do I mean by the rule? Basically a formula that tells you how to get any term in the sequence, right? You could think about it. What if I tell you, okay, take the sequence that starts with 11, and then to get the next term, you add 7. So most of you would go, okay, so I start at 11, and then I add 7. Then I add 7. Then I add 7. Well, that's great, but what if I ask you for the 10,000th term of that sequence? You don't want to sit there and add 7, add 7, add 7, 10,000 times. That's ridiculous, right? So what we want to be able to do is come up with a formula that gives us the 10,000th term of the sequence. And we kind of have that up here. That's what they've given us right here. This is a formula that gives us the nth term of the sequence. Okay, so how do you look at this? Well, you look at, here's our n, here's our input. So here's the, it's kind of weird. It throws people off that the first term is actually starts with counting 0. This is how computer scientists count. They start counting with the number 0, and it sometimes can be confusing. You get what's called in computer science an off by 1 error because they like to start counting at 0. So just keep that in mind. The term that sends 1 to something is actually the second term. That's why I think it's kind of a weird way to represent it, but you do see it. And I think that's probably wise because of computer science, why some books prefer to do it this way. But look at our actual sequence of numbers, right? This is our a sub n row, meaning this is a sub 0, this is a sub 1, this is a sub 2, this is a sub 3. Well, look what happens for any of these terms. Take any one of these terms. How do you get to the next term? It looks like you subtract 2. So that's an easy way to find the common difference for an arithmetic sequence. You just take 2 consecutive terms, and you just ask yourself, what do I have to add to get from this term to the next one? Right? So what do I add to -3 to get -5? I add -2. Right? And you can see that's what they do down here. They take 2 successive terms, and it doesn't matter which ones you pick as long as they're consecutive. Right? We could do it right here. How do you get from -5 to -7? You add -2. Right? So you can see that it's consistent for all of these. To get to the next term, you add -2. Okay, so there's our common difference right there. So you can see they go, oh, d is equal to -2. That's the d from up here. That's this d in our formula. You get that d by just looking at the common difference between 2 consecutive terms. Okay? Now what they do is they grab that formula, the one that's right here. They grab this, and they've got it right here, except look, they turn the d into the -2. You plug it in right there. And then what about a sub 0? Well, a sub 0 is given to us in the problem. We have that information. It's -1 right there. So you take it, you plug in your -1, and then you say, well, let's see, what were we trying to find? Find the rule, and then use your rule to find a sub 10. Okay, right. So then you simplify this. So a sub n is equal to -1 minus 2n. There's our formula in general. So we can use that formula like I mentioned earlier. What if I said find the 10,000th term? Well, we wouldn't have to keep adding -2 10,000 times to get the 10,000th term. We can just use this formula to get it right away. Okay? And that's what they do down here. A sub 10 is equal to -1 minus 2. Now for n, they've plugged in 10, and they get -21. So that's helpful. You don't have to sit there and write out the first 10,000 terms. You could just jump right to the 10,000th term. Right. Okay, so what about this? I don't know why it keeps making me blurry this morning. Usually that happens if I move around too much, but I don't know what's going on. Okay, so what if you have to find the rule and you don't have consecutive terms? Like up here it was easy because we could see all these consecutive terms and it was pretty obvious, oh, you add -2 to get the next one, right? Well, what about down here where they tell us, suppose 2 terms of an arithmetic sequence are a sub 8 equals 10 and a sub 12 equals 26. What is the rule for this sequence? Well, in this case, we don't have consecutive terms, right? So what I'll tell you is there's lots of different ways for writing problems for sequences, specifically sequences. Series a little bit too, but those follow the formulas a little bit more. So don't think about trying to memorize certain problems. Just understand how sequences work and then treat it like a puzzle. Treat it like a, some kind of word puzzle or something like that where, like Sudoku where you have to kind of work at it a little bit, some kind of game. Just treat it like that. You have certain information and you have to try to figure out how to get the missing information. Don't think of it as like, oh, yeah, he didn't show me how to do this exact problem, because there's so many variations of these problems. The key is to understand what your toolbox is full of and then be able to use those tools to find the missing information, right? It can get frustrating if you think of it as like, well, I didn't memorize this particular type of problem. Just try to puzzle your way through it. So what you want to do is this is kind of how I do it, something off to the side. They're telling us that when n is 8, then our sequence term is 10. And then they're telling us, so what do? Well, you would add d to get the 9th term, add d to get the 10th term, add d to get the 11th term, and add d to get the 12th term, but they tell us that that's 26. See? So you start with 10, you add d again, you add d again, you add d again, and we know that 10 plus 4d is 26 because that's what they told us in the problem. A sub 12 is 26. But now you have a formula that you can go through and solve and say, well, if I started with 10, that was a sub 8, and I added d 4 times, and that ended up being 26, then if you solve this equation here, you end up with d equals 4. So that's great. We just got our common difference. So even though we were not given consecutive terms, we were still able to easily get that common difference. And you know, when I do these problems, I write this out. I see students try to do this in their head, and I don't know why. I cannot figure out why students try to do this part in their head. I mean, occasionally it works, but I see a lot of people make a lot of mistakes when they're trying to do this in their head. If it's me doing a problem like this, I just write it out. Right? I go, okay, 8 is 10. 9 is 10 plus d, 10 is 10 plus 2d, 11 is 10 plus 3d, 12 is 10 plus 4d, and that equals 26. Like, sure, it takes you a few extra seconds to write it down, but you're going to save yourself a ton of time. That one time you make a mistake is going to be, it's going to cost you a ton of time. So it's usually just easier to write it down, right? You're not saving yourself work or time by not writing it because you're going to end up making a mistake. Okay, so let's see. What are we supposed to do here? What is the rule? Okay, so we've got that d is equal to 4. We know the common difference is 4. So now we just have to figure out what the original term is, right? What the very first term is. Because we've kind of got this a sub n is equal to a sub 0 plus 4 plus, n times d. But we already know that d is 4. So the thing we have to figure out is a sub 0. So this might look kind of confusing where you're like, well, what's going on here? What they're doing here is saying, well, a sub 8 is equal to 10. So they're just plugging those values in. A sub n is 10, and n is 8, and then you solve it from there. The other thing that I see people do, and this actually is fine, I do this sometimes when I'm figuring these problems out, just work your way backwards. If you know the common difference, and you know that a sub 8 is 10, then just work your way backwards using, you know, in this case, you'd be subtracting 4 because the common difference is you were adding 4 every time. Just work your way backwards to a sub 0 and figure out what your original term is. So this is what I mean is don't worry about memorizing these problems. If you understand them, there's more than one way to do these problems. And for some of you, this is going to make perfect sense right here, and you're going to go, oh, okay, I can remember to do that. That makes sense to me. And some of you are going to go, oh, well, if I know the common difference, I'll just work my way backwards and figure out what the original term is. They're both perfectly legitimate ways to do the problem, and they're both fine. So whichever way makes more sense to you, you should do that one. Okay. Okay, so that's how you're going to deal with those. Sometimes they're going to give you consecutive terms, and then all you have to do is use subtraction to get the common difference. Here they're giving you terms that are not successive, and all you have to do is just sort of think your way through how you got from one to the other, and then go through and solve them. Okay, so that's arithmetic sequences is when you add the same thing every single time to get the next term. So like in this case, you're adding 4 every single time to get the next term. Okay, geometric sequences are similar, but there's a difference in that geometric sequences are where you're going to multiply by something to get the next term. Okay, so maybe you multiply by 3, right? You start at a certain number like 4, and then to get the next term you multiply by 3. So you'd start with 4, okay, and the next term you multiply by 3, that'd be 12. Multiply by 3 again, 36. Multiply by 3 again, you'd get what, 108 or something? So you see what I'm saying? You start with a specific number. Now you're multiplying every single term. That's called a geometric sequence. So let's see that formal definition. You're going to see it looks kind of like the way you think about this problem. you can think about it in the same way as an arithmetic sequence, except you're using multiplication instead of the addition that we used previously. So a geometric sequence is defined by the rule a sub n is equal to a sub 0, that's our original term, our initial term, times r to the n. So before it was n times d, now it's r to the n. Where basically r is the number that you're going to multiply by every single time to get the next number. So it says where a sub 0 is the starting value of the sequence and r is the fixed number by which any term of the sequence is multiplied to obtain the next term. If r is not equal to 0, this is equivalent to saying that r is the common ratio of successive terms. So remember previously we subtracted two successive terms to get the common difference. Now you will divide two successive terms in order to get the common ratio. So it's a similar idea. We're just dealing with multiplication, whereas a minute ago we were dealing with addition. Okay, but it's very similar. So if you have two consecutive problems, this is pretty easy, right? Because we can see, find the rule for the geometric sequence with terms a sub 2 equals 12 and a sub 3 equals 24. So you go, okay, well, how did I get from 12 to 24? Well, I multiplied by 2. And you can see they do that right down here. They divide them. 24 divided by 12 equals 2. So that's how you figure out that common ratio. So then you take your formula, a sub n is equal to a sub 0 times 2 to the n, because we know the common ratio is 2. So we plug 2 in there for r. And then you take some value that you know. So we know when n is 2, a sub 2 is equal to 12. So you plug those values in, solve for the common ratio. Or sorry, we already got the common ratio. Solve for the initial value. And then you just plug them in, and here's your formula in general, right? A sub n equals 3 times 2 to the n. So there's your formula that you're dealing with. What if you have two non-consecutive terms and you need to find the rule? Well, you basically just model the problem we did a few moments ago, except now we're multiplying instead of adding. So what you'll do over to the side, they give you, let's see, we have a sub 2 equals 32, a sub 5 equals 4. So just map it out. Okay, if I start with a sub 2, that's 32. Then I would multiply by r to get the next term. I would multiply by r again to get the next term. Multiply r to get the next term, but that's the one we know, which is a sub 5, which we know is 4. So then you have this equation, 32r cubed equals 4, and you're just going to go through and solve that. So if 32r cubed equals 4, you know, divide everything by 32, take the cube root, you're going to end up with r equals 1/2. Okay, so that means the way this sequence works is each time you multiply by 1/2. That's how you get the next term, is you multiply by 1/2. And then like we've been doing, you just plug in one of these initial, or these given points up here, the two values, a sub 2 equals 32, plug that in and you can solve for your very first term of the sequence. And now you have your formula for finding the nth term of the sequence. So if we said, what's the 10,000th term of this sequence? Well, we could figure it out. Now it's going to be very, very tiny because of 1/2 to the 10,000 would be tiny, but you see the idea, right? Notice if your r is less than 1, then your geometric sequence will be getting smaller, right? If it's because if it's bigger than 1, like 2, then your terms are going to get bigger. If it's smaller than 1, like 1/2, and you're multiplying by 1/2 each time, your terms are going to get successively smaller. Okay. So we've got applications of arithmetic and geometric sequences. There's all sorts of them. There's actually a ton of things, a surprising number of things. When you first learn about these, you kind of go like, when would I use that? Like they get used in science all the time. That comes up here. They're talking about like harmonics or strings of like a violin or something, and the vibrations of those strings, DNA fragments. So there's lots of different places in which you can use these. Also, finances can do this, right? If you think about like, if you're getting interest on some kind of an account. Well, each term in your sequence could be the money that is in your account at the end of 1 year. And depending on how that interest is being applied, it might be a geometric sequence, right? Let's say you're earning 3% on your money every year. Well, then you could use a geometric sequence where the number that you multiply by would be 1.03. You've got your original money plus 3%, so 1.03. So in finance, this kind of stuff comes up too, right? Depending on what kind of finance you're in. So lots of different places those sequences and series come up. So you'll see you have some homework problems where they have you go through, and you're basically, it's like the problems we just did. So if you get stuck with those, check out the examples in the book. They have some written examples here, it looks like, where they write one out and they kind of give you an example for how it works. So use those. But let's move ahead to 7.2. So now we get into this idea of sums of a sequence. So what happens is, under certain conditions, you want to add up the terms of a sequence, right? Sometimes you don't. Sometimes the sequence represents something in a way where you don't want everything added up. You only need to know the term that corresponds to that particular thing. Like if it's an investment, like I mentioned, where you're getting 3%, and you want to know, well, how much is going to be in this account in 40 years? Well, then you really only care about the 40th term, and you look at it, and that tells you how much is in the account in year 40, right? But there are other times where you want to add up everything that's in the sequence and see what the total is. And the good news is there are some interesting, under certain circumstances, there are some very interesting problems that can arise by doing that, right? They kind of start off with the 12 Days of Christmas song and sort of representing that, but I think we'll skip that for now. So we have the sum of terms of an arithmetic sequence. Okay, so there's a pattern that arises that they want you to see that gives rise to a formula that's easy for us to remember. And this is one where you can memorize it, but also you can just understand what's happening, and it makes it a little bit easier. Let's say you want to add up the numbers from 1 to 12. Well, notice if you take the first number and the last number and add those up, you get 13. And then you take the second number and the second to the last and add those up, you get 13. And then you take the third number and the third to the last number, and you get 13. So guess what would happen if we added the fourth term and the fourth to last number? You probably see what's going on. You get 13. So as you follow that pattern, you keep adding up to 13 the whole time. So what happens is, as we do that, we can sort of create a formula for it, and you end up with this. I'm not going to, they kind of derive it here in the book. I'm not going to take the time to go through all of it. It's interesting to see how that comes about. It's one of those sort of explanations that isn't, it's not like crazy advanced where someone's going to necessarily get lost along the way. But for the sake of time, I want to keep us on the stuff that's going to help you get the homework done. So the key is, if you want to add up the numbers from 1 to n, so 1 to n, we get this formula. It's n times n plus 1 over 2. Okay. So if someone's like, there's a famous story, you never know if these things are true or not, but there's a famous story about a famous mathematician named Gauss, who was very famous. He made incredible contributions to mathematics, and he died at like 21 in a duel. Right, so that's kind of amazing that by 21 years old, he was able to make like incredible contributions to mathematics. And you kind of wonder, well, what would he have done if he hadn't died at the age of 21 in a stupid duel, right? But there's supposedly in like the first grade or kindergarten or something, Gauss was acting out in class, and his teacher said, "Go add up the numbers from 1 to 100." And then come back when you've figured it out. And it was just to keep him busy. And then he immediately told her what the numbers 1 to 100 added up to, because he knew this formula. Like he had already kind of figured this out on his own. And he just said, "Oh, here's the answer," because he was doing this calculation, n times n plus 1 divided by 2. So that'd be what? 100 times 101 divided by 2. and he was pretty good with numbers, so he could do that in his head, and then he just gave the number, right? Who knows if that actually happened, but that's supposedly what occurred. So that's convenient. So we have this new notation where we have S sub n. S sub n tells you that S is for sum, right? It means the sum. So S sub n means add the first n terms of a sequence. So notice this is not any particular, like this formula here is for one specific sequence, the natural numbers, where it goes 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, up to whatever your n is. But we want to figure out how to do that for any sequence, not just this one, the natural numbers that we're used to, but any sequence that we're given, right? So when you see S sub n, you go, oh, if that means for the sequence that we're talking about, I want to add up the first n terms of that sequence. And luckily for us, there's a nice little formula for that, and it's given right here. So the sum of the first n terms of an arithmetic sequence. So whenever you're doing this chapter, the first thing you do when you look at a problem is ask yourself, is this an arithmetic sequence or is this a geometric sequence? Because the tools that we use are different, right? The problems are similar. Remember earlier we did 2 sets of problems, and the only difference was really whether you were adding or multiplying to get the next term. It just changed the problem a little bit, but it was the same basic idea, the same basic structure to get through the problem. So you always have to ask yourself right out of the gate, is this arithmetic or geometric? Sometimes they'll tell you in the problem. Sometimes you have to figure it out by looking at the sequence or by getting clues that are given inside the problem. But that's kind of you always are going to have to know what kind of sequence you're dealing with right from the start. So they're saying, let's say we have a sequence and it's arithmetic. So it's just, it follows this. This is our form for arithmetic sequences right here, right? So that's all they're saying. It looks complicated, but they're just saying it's an arithmetic sequence. And let n be a positive integer, of course, because we're not going to ask about the negative 4th term of the sequence. That doesn't make sense, right? So basically, we have an arithmetic sequence is just all that first sentence is saying. The sum of the first n terms of the sequence, a sub 0 through a sub n minus 1, right? And you might go, well, wait, why are we only going to a sub n minus 1? Why aren't we going to a sub n? That's because we're starting counting by 0, right? It's that weird computer science counting where you start at 0. So, you know, like you can see it on one hand. If you start counting at 0, 0, 1, 2, 3, 4. Notice how I got to 4, but I have 5 fingers up. That's because you started counting at 0. So it's that off by 1 that computer scientists like to do. This is given by the sequence, or the sum of the first n numbers, which is a sub 0 plus a sub 1 plus a sub 2 all the way up to a sub n minus 1, is given by this right over here. N divided by 2 times a sub 0 plus a sub n minus 1. So basically you add the first and last term of the part you care about. So if you care about the first 100 terms, you take the first term plus the 100th term, you divide it by 2, and you multiply by n. So that formula is pretty straightforward. There's another version here that you can do. So you go, wait, what's this one over here? This is like, what if you don't know what the nth term is? What if you don't know the 100th term of that sequence, if that's what we're trying to find? Well, this is how you would get it right here, right? So either one of these is a convenient way to get your summation, depending on what information you have. If they give you a problem where they say, here's the first term, here's the 100th term, find the sum of the first 100 terms, then you'd use this second one. If they just said, here's the sequence, here's our first term, then you'd probably use this first one, right? So if you're having trouble getting one to work, try the other one, is basically the bottom line. So find the sum of the first 11 terms of the arithmetic sequence. So I'd look at this and say, okay, they're telling me it's an arithmetic sequence. That's helpful. And when I look at it, it looks like my common difference is what, 3? Right? It looks like you add 3 to get the next term. So you go, okay, so, and they're starting with 2. So that means I know the formula for my arithmetic sequence. It's 2 plus 3 times j, right? They were using n. I don't know why they're switching to j now, but they're switching to j. So the jth term is 2 plus 3 times j. Okay? So now you just they're taking this formula right here, and they're plugging in. A sub 0 is 2, so they plug that in. They're plugging in n, which is, let's see, what do they want? The first 11 terms. So that means they're using n now for that, which is fine. So n becomes 11. So 11 goes here, 11 goes here. They plug in all the values. You've got your initial condition. Your D becomes a 3. So they're just taking the information we gathered, plug it into the formula, and it all simplifies to 187. So if you wrote out this sequence to 11 terms and added them all together, you should get 187 is what that means. Okay? So that's it. So now you can see it gets a little more complicated. Calculating the sum from the initial and final terms, well, that's where you're going to want to use that second one. If they just give you the initial and the final terms, then use that. So find the sum of all even numbers between 2 and 100 inclusive. So, you know, you take the numbers here, you add them up. How many numbers would there be? If it's even numbers between 2 and 100, that's 50 terms. So n becomes 50. You've got your first term is 2, your last term is 100. Plug it all in there, and you get 2550. Okay? So just use whichever of these two versions is more convenient for the problem that you're working on. And it depends on which information they give you in the beginning. Okay? Now we have this thing that is it looks more complicated than it is, right? It looks like we're starting to get some like hieroglyphics here or something that we don't really understand. Notation can be very confusing in mathematics. This problem is much easier than it seems. Why is that? Because all this capital sigma means is add stuff up. When you see this symbol right here, it means you're going to add some things together. That's it. Okay? Now we have, it's slightly more complicated than that, but don't overthink this. We're going to add some things together. Okay? So that's called summation notation. So let's take a look at this version right here. Okay, so the number that's below the sigma, that's your starting value. That's your initial value for the index. And that initial value can start at, commonly it starts at 0, or commonly it starts at 1. Those are the two most common starting points that you're going to see, is that I starts at 0 or 1. But it is not uncommon to see that I started another value, like 7 or 5 or even -3 or something like that. Okay, it can start at any value, any integer value, but it usually starts at 0 or 1 for most problems. So you start at I, in this case I equals 1, and you plug it into whatever expression is over here, in this case I squared. So they're telling you what to do with your I. So when I is 1, we square it. 1 squared is 1. Now we're going to add to it each time we iterate. So now I go back down here and I iterate. That means we're going to add 1 to it. So I goes to 2, and this says now we're going to make it 2 squared. So that's 4. So we have the 1 we got the first time. Now the 4 we're getting the second time, so that's at 5. Okay, now I is going to go to 3. Well, 3 squared is 9. So we had what? We had 5. We're adding 9. Now we're at 14. So we just keep squaring numbers, and we keep adding that to the sum that we previously got. Okay? And you just keep doing this until you get to the number at the top. This tells you when to stop. So when your I hits the value that's up here, that means that's your last step. You're about to end. Okay? And that's all that means, right? And I know that the way I just said it sounds a little like it's actually kind of complicated, but you'll see, like, once it clicks and you get it, you're like, oh, I'm just adding some numbers up. That's not really a big deal. So for example, what would we do here? So this says the sum from I equals 2 to 5 of 3i. Okay, so we'd start with 2, and we'd plug it in there. Go 2 times 3 is 6. Okay, now I equals 3. We go up by 1, so I equals 3. Now we plug 3 in here. Okay, 9. So we had 6. We're now adding 9, so that puts us at 15. Okay, now I goes to 4. We put it in here, 12. So we're at what? 15 plus 12, so it's 27. And then your last one, we go I equals 5. Now notice that matches the one up here, so that means this is our last step. We're going to stop because I has reached 5. You plug it in here, you'll get 15. You'll add that to your previous sum. So you get all those numbers added up, and you're done. So you can see that's what they did right here, right? We plugged in 2 to get 6. You plug in 3 to get 9. You plug in 4 to get 12. You plug in 5 to get 15. And since I equals 5 now, this number on top, we stop and we're done. So you add all those up and whatever that comes out to, right? That's going to be what, 42 or something? Then you're done. What about this one? This one actually throws people because there's no I in it, and people get a little bit confused. So what is this saying? This is saying start at I equals 3, and you're going to keep iterating until you reach an I value of 6. And what are you adding up each time? 7. There's nothing to plug that I into. You're just adding 7. So this is saying just repeatedly add 7. Okay? So that's why right here it just becomes 7 plus 7 plus 7 plus 7. Okay? So, you know, they're giving it's a nice convenient way to write a sum because as you could see here, this sum has 10 terms in it, right? And sometimes you get into terms where there might be thousands or even more terms that you're adding together. Obviously, you're not going to write that out in a big string, right? It would take pages and pages and pages, and it wouldn't really be very, very helpful for you to have that written out. But look how compactly we can write really large sums in a nice, compact, easy to understand way. So this has 10 terms in it. I equals 1, then 2, then 3, then 4, then 5. I equals 6, 7, 8, 9, 10. So that's 10 terms. Well, rather than writing out this big string of 10 terms, we can just write it like this. That's much more convenient. Okay. So that's one reason that we like this sigma notation is it's much easier to deal with these sums when they're written in that way. Okay, so then we have sum of terms of a geometric sequence. So we've got our rule here, A0 R to the J. Remember, that's how we write a geometric sequence. And we want to add the first n terms, so it's going to start at j equals 0. Oh, it doesn't always have to be I. It can be a j. Actually, sometimes people use k. You can use m. You can use any letter you want. You probably aren't going to use o because it can look like a 0. But, you know, the point is it doesn't matter what symbol you use to represent the variable. It's just that's the thing you're going to iterate over. So in this case, you would start with j equals 0, and you'd plug it in here. Okay, j equals 1, plug it in here. We don't have the r value or the initial value, but you get the idea. We're doing the same thing that we did before. So if you go through all that, you end up with the sum of the terms of a geometric sequence. And actually, this is titled kind of poorly. This should be the finite sum of terms of a geometric sequence because there's two types of sums we can have with the geometric sequence. Remember, this notation says we're adding up the first n terms. The first n terms of that thing. So we've got a sub 0 r to the j. So j is equal to 0. We're summing from j equals 0 to n minus 1, so it's the first n terms, and we're going to add them all together. That's what the sigma means. So this s sub n, since we know it's a geometric sequence, a sum in this case because we're actually going to add them together, this makes sense right here. This is just the mathematical way of understanding what this s sub n is representing. And there's a nice little formula here. It's you take your initial term in the sequence, you multiply by 1 minus r to the n. So remember, r is that common ratio. So you have 1 minus r on the bottom, 1 minus r to the n on top. Simplify everything, and you'll have the first terms of that sequence. So here's a problem. Find the sum of the first 5 terms of the sequence. A sub j is equal to 1/2 3 to the j. So we want to know what the sum of those first 5 terms are. So you're going to take, okay, s sub 5, that's the sum of the first 5 terms. We know that r is 3 because we can see it here in the formula that we're being given. We know that n is equal to 5 because we want the first 5 terms. And we can also see that our common ratio is 1/2, or sorry, our initial term is 1/2, right? So then you just take all those pieces figure out your a sub 0, your r equals 3, your n equals 5, and then you just plug them into this formula right here. So you can see that's what they do. 1/2, 1 minus 243, because that's 3 to the 5th, over 1 minus 3, simplify everything, and you get 121 halves, right? So it's what, 60.5? So that's a pretty easy formula to do. The hardest part for most people is going to be identifying the a sub 0, the r, and the n. Once you get that, it's real easy. You just plug it into the formula and figure out, what to do from there. Like, do your simplifying in whatever way you're supposed to. So one thing you can do, there's a few things you could do. One thing that you should realize is there's more than one way to write this sigma notation. So notice how they started here with j equals 1, and you go to 5. What you could do, you can make an adjustment. If you modify things correctly in your formula right here, you could make this start at j equals 0 and have it go to 4. So instead of going from 1 to 5, it would go from 0 to 4. But you have to make an adjustment over here in the formula. Okay. The other thing that they have you do in this problem is basically you write out the terms that you're interested in, and then that can help you rewrite things, right? So if you're ever missing something, just see if, unless it's asking for the 1,000th term, then you're not going to write out the sequence. But if it's asking you for like the 7th term or something, just figure it out by hand what that 7th term is if you're having trouble with it. So that's what I mean. There's lots of different ways to do these problems. It just depends on, there's so many variations of these problems where we give you certain information, you're missing some information, and depending on the type of sequence it is, if it converges or not, there's lots of variations. Now here's where things start to get a little bit weird. So for those of you who are going on in math and you're going through the STEM track, so that's calculus and linear algebra and differential equations and onward, what happens is you start running into infinity in these classes, and each time you run into it, it's going to get weirder and weirder, right? You're going to do things in Calc 1 with infinity that are going to be very confusing to some of you, right? You're going to find it very strange. So infinity is just kind of a weird thing. People like to think of as infinity as a big number, and it definitely is not. It has some very strange behavior. So this is kind of your first introduction to when infinity gets weird for the first time, and that is this idea that we can add up an infinite number of numbers sometimes, and they add up to a finite number. Like, that sounds weird. I could take an infinite number, I could add up an infinite list of numbers, and it can add up to like 3. What if they're all positive, right? It's one thing if you could say, well, what if some of the numbers are negative? Then that makes sense. It could add up to 3, and that's a good observation. But what if we take an infinite list of positive numbers, and they all add up to the number 3? That weirds some people out. But as you'll see, it is definitely possible. So if the absolute value of r is less than 1, so remember we talked about that r value 0. If your r is greater than 1, then the terms in your sequence are going to get bigger and bigger and bigger. Like if r is equal to 2, then the next term will double, right? Every next term is doubling. So when you add up all those terms, you're going to get really, really big numbers, right? And if you add up an infinite number of them, it's going to go towards infinity. But what if we have r less than 1, or in this case, the absolute value of r is less than 1, like say 1/2? What if to get the next term is 1/2 the number before it? Then our numbers are getting smaller and smaller and smaller. They're shrinking down. In this case, we can add up an infinite number of them, and they add up to a finite number. And I know this seems kind of weird. So if the absolute value of r is less than 1, that basically means r is between -1 and +1. Then the infinite geometric series, a sub 0 plus this is a sub 1 is a sub 0 r, right? And a sub 2 is a sub 0 r squared. A sub 3 is A sub 0 r cubed, and so on. So we're adding up an infinite list, not a finite list. We're adding up an infinite list. We already did the partial sums, the s sub n. Now we're adding up an infinite list of numbers. And we write it this way, S. Notice how there's no N here. This is just S for the sum. That means the sum of the entire list of the infinite sequence of numbers. So we start with the sum from I equals 0 to infinity of the terms in our geometric sequence. And they add up to, look how nice this formula is. It's a subtraction and a division. That's nice, right? So you need to know the first term of the sequence, and you need to know the R value. That's it. Those are generally going to be easy to find. You plug it in this formula right here, and it tells you the sum of that infinite list of numbers. So it's something that sounds like it's going to be hard to calculate, actually not bad. Pretty straightforward. So let's take a look here. So let's look here. 2 plus 4 plus 8 plus 16. Okay, so what's our R value here? It's 2, because each time the numbers are doubling. Well, if we had this infinite list and we added them all up, then they're going to go towards infinity. There's not a finite number they're going to add up to. Okay? But what about over here? Well, here, to get the next term in the sequence, we're multiplying by 1/2. And 1/2 fits this. 1/2 is between -1 and +1. So it fits this condition up here. That means when we add up this infinite list, we're going to get a finite number. So here's that formula. S is equal to A sub 0 over 1 minus R. Well, what's the first term in our sequence? It's 1. So that's what's going in the numerator. And what is our R value? Well, it's 1/2. We just talked about that. So you just plug those values in. You get 1 over 1 minus 1/2, which is 1 over 1/2, which equals 2. So this sequence, if you could come up with the infinite list of this sequence going on forever, and you added up all of those fractions, they add up to 2. The number 2. Like, if you look, that's not a lot of work in order to do an infinite addition. And we just figured it out. And like, look, there's not very much black right here, right? Not a lot of writing going on like right here, right? So then they give you a different problem. Find the following sum. 2 plus 1/2 plus 1/8 plus 1/32. So I look at this and go, okay, it looks like our first number is 2. So A sub 0 is 2. So that would go in the numerator. And then it would be 1 minus R. So what's R? So you look at this and you go, well, what am I multiplying by to get 1/2? What am I multiplying 1/2 by to get 1/8? What do I multiply 1/8 by to get 1/32? And the answer is 1/4. Right? 1/2 times 1/4 gives us 1/8. So then you would stick 1/4 in here for R, simplify it just like you see in this problem, and you'll have your value. Okay, so not too bad. And this one seems kind of weird. Like, why would we need an infinite sum? Oh, here's that retirement problem I was telling you about earlier. So here's some more problems involving seating capacity. Here's some more problems involving those finite sums. Looks like they don't have examples for the infinite sums. Some of those get to be a little bit more advanced for the infinite sums, but they definitely are important, and you'll see these things again like in Calc 2. You'll see them from there. Okay, so that's how those work. And let's see, general sequences in series. Okay, so 7.3, we have some sequences in series that come up a lot that are not arithmetic or geometric. So arithmetic sequences, very important. They come up frequently. You want to know how to deal with them. Geometric sequences come up frequently. You want to know how to deal with them. But sequences don't have to be in that specific form. Sequences can be all sorts of things. So let's take a look at some of those examples. Okay. Generating a sequence from a rule is pretty straightforward. You just follow the rule, right? So using the first few terms to find the sequence, well, just look at it. Like, look at this first one. Does it look like we're adding the same thing each time from 1 to 8. That would be what? I would add 7. Does 7 get me from 8 to 27? No. Does it get me from 27 to 64? No. So it would indicate to me that this is not an arithmetic sequence, right? In fact, in this case, it's not a geometric sequence either. How do I get from 1 to 8? I'd multiply by 8. Does that give me to 27? No. Okay, so you can kind of see, well, then this must be some other type of sequence going on, right? So then this is where some of you are going to, this is one place where some of you will find this not very challenging. Others of you will find it easier. It kind of comes down to your number sense. There's a question in the chat about what you need to bring to the test. You need to bring your ID so you can get in there, a calculator, and something to write with. You don't need a Scantron or anything because you're actually going to write out your work and get partial credit and stuff. Okay. So what you want to be able to do is recognize this and go, oh, that's the cubes of the first, like, whatever terms, right? So some people will recognize right away that these are cubes. It's like a puzzle game. You're trying to figure out what the pattern is and go, oh, I recognize all those are cubes. And then you go, oh, okay, so it's n plus 1 cubed, right? And then this one down here, you look at it and go, oh, these look like squares down here in the bottom of the denominator. So it looks like, 1 over n plus 1 cubed, or n squared, 1 over n squared. So you basically are going to work through those, right? Then we have what are called alternating sequences. So this is where you have a positive followed by a negative, followed by a positive, followed by a negative. And how do we represent that mathematically in a sequence? Well, the key is that you use this, -1 to the n. Because notice when n is even, then you're getting -1 to an even number, which makes it positive, and it just is 1. But when n is odd, then you have -1 raised to an odd power, and it makes the whole term negative, right? So, so that's one way in which you can make them oscillate. 1, -1, 1, -1, positive, negative, positive, negative, positive, negative. Now you might be looking at it going, right, but what if you want to switch which terms are positive and which ones are negative? What if, like in this case, when we put in 0, we're going to get 1. Then when we put in 1, we get -1. Then when we put in 2, we get 1. What if we want the other terms to be the -1? Then what you do is you raise it to -1 to the exponent n plus 1. And it just shifts over by 1, which ones are positive and which ones are negative. So depending on which terms you want to be positive and which ones you want to be negative, you either make it -1 to the n or -1 to the n plus 1, where the plus 1 is in the exponent as well. Okay, if you do that, then you can end up with either of these. See how they have one where it goes 1, -1, 1, -1, 1, -1? But then one where it goes -1, 1, -1. So where the negatives are has been shifted by 1. You just would make the exponent n plus 1. That'll fix it for you. This you should be able to do. Here they're just giving you a formula and saying plug in n. That's not tricky at all. That's pretty straightforward. You can graph sequences. Notice that when we graph sequences, you're not getting like a whole curve because it's only these specific points, right? So make sure if you're looking at a graph or you're doing the graphing that you understand you're only graphing those integer values. You're not graphing like we're used to having a whole curve or a line or something in there. You're not doing those. Recursively defined sequences can be very interesting and they can be very powerful. Some of you will, if you're going into computer science, you're going to do a lot more work down the road with recursive defined sequences. In computer science, like in programming languages, you can generally actually define recursive functions, which are kind of amazing sometimes. You can write one tiny little function and it recursively acts on itself. And it does an incredible amount of calculations in like 2 or 3 lines of code. It's kind of amazing. Sometimes I get a little confused when it takes me a few minutes to kind of figure out how to set them up because they can get a little bit confusing writing code for recursive functions, but they can be very powerful. So basically what you have with a recursively defined sequence is that the terms are based on the terms that came before it. So the most many of you may have already heard about the Fibonacci sequence. So the Fibonacci sequence is where you take the two previous terms and you add those together to get the next term. So there's two conditions for this. One, you need a rule that tells you how do I find a sub n based on the terms that came before a sub n. So that's one thing you need, is a rule telling you what to do. The other thing you need is what they sometimes call the seed terms. Seed, like seed for a tree. The seed terms are you need enough terms to get the sequence started, right? So in this case, our term is only based on the term that came before it. So we only need the first term defined, because once we want to know a sub 1, then we just base this on a sub 0. We calculate this, see what it is. If we want to know a sub 2, we'd use this formula on a sub 1. If we want to know a sub 100, we'd base this on a sub 99. Okay. But the Fibonacci sequence uses the two previous terms. So that means you'd need the rule for the Fibonacci sequence, and then you would need to include the first two terms of the sequence, right? What if you had a sequence that was recursively based on the previous 4 terms? Well, then you would need the rule, and then you would need the 4 starting terms to get the sequence started. You have to have enough to get your, it's kind of like when you prime a motor to get it going or whatever. It's the same thing here, right? Or an engine or whatever. Yeah, so here they have the Fibonacci sequence. So here, the Fibonacci term is based on the sum of the two previous terms. Well, then we need at least 2 terms to get this thing started. So they give you f sub 0 equals 1, f sub 1 equals 1. Okay, so if I want to know f sub 2, then I take f sub 0 plus f sub 1, add those together, and you can see, like, 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5, right? 3 plus 5 is 8, so we'd know what the next term, it would be 8, and it would go from there. Okay, so that's what recursive functions do. They're based on the ones that come before it. Now, it's trickier. Like, you could imagine it would be hard. What if we asked for the 100th term of the Fibonacci sequence? Well, we don't really have a formula for just plugging it in. I mean, you can come up with one, but it's much more complicated than the problems we did so far. So, finding the 100th term of the Fibonacci sequence is a little more work. In fact, the easiest thing to do would probably be to write some computer code and just say, calculate, here's how you calculate the terms of the sequence, calculate the first 100 terms for me, and then give me the answer, is probably how you do that. Here we have partial sums, which is kind of what we were talking about earlier. Like with S sub n, it's basically that. The nth partial sum is just the first n minus 1 terms, or the first nth terms of that summation. And then there's some applications to this. So again, this stuff has lots of applications. So that's the main thing here. You have your general sequences where you want to play around, find things where they're not arithmetic or geometric, be able to recognize those. And it's, again, just treat it like a little puzzle. It takes a little practice, but you'll get the hang of it. And then being able to know how do we handle alternating sequences. And the key is just -1 to the n or -1 to the n plus 1, either one of those. And then you've got your recursive functions where they give you a rule and they give you the terms to get things started, and then you just go from there. Okay? So that wraps up the material that we have due. So make sure you're working on those homework problems. I will check and kind of make sure people have enough. I'll probably check again tomorrow. Make sure people have enough late passes. If you need a late pass, send me a message in Canvas, and I'll go in and I'll reset everyone's back to 20 or whatever. And then you should be good to go. But make sure you get all those homework points. Make sure you get your test taken. Make sure you get that taken care of, right? Because I'm going to try to pick those tests up tomorrow and grade them over the weekend. And I'm supposed to have grades turned in on Monday. So moving forward with that stuff. So make sure you get all that taken care of. Again, great job if you made it to the end. You sacrificed your summer or a large portion of your summer in order to pass this class, and you made it to the end, so good job. Hopefully I can give you a passing grade, and it will all end successfully for you with a passing grade in this class, and you won't have to take it anymore. I hope that I can give everyone who takes this last test a passing grade, but that doesn't always work. So thanks everybody. I know a lot of you have worked very, very hard. And again, you should feel good about that. It's not easy taking these classes in the summer. It's very, very difficult. So good job to you for completing it, right? As I don't know if, I guess it's not as obvious in there, but I can see many people who started this class are not still in it, right? Not everyone made it to the end. It took hard work to get to the end. So keep that up. That's a huge part of being successful in school. It's just putting in the hard work that other people are not willing to do. A lot of times is the difference between succeeding and not succeeding. So hopefully you're all sort of either have learned that lesson or you're learning it right now, that half the game is just the hard work, and go from there. Right. So thanks everybody. Make sure you get your test taken, and try to enjoy a few days after the class ends. Like finish up the next couple days and get your get your homework taken care of, so you get every homework point that you can. So for some of you, those a few homeworks might make the difference between passing or not passing and going completing the course successfully. And make sure you get the test taken. So as always, I will be in Zoom. I'm going to shut down the YouTube stream, but I will be in Zoom if anyone wants to come talk to me. Okay, thanks everyone.